Many of the unanswered questions lie on the interface between particle physics, astronomy and gravitation. STAG was formed to try and facilitate this research at the interface. So there's a lot of interaction, students working across the boundaries with expertise and supervision.
My research concerns the accelerating expansion of the universe, the rather puzzling observation that instead of slowing down as gravity pulls everything back together, the universe is instead accelerating in its expansion. There can, in principle, be an accelerating effect caused by non-uniformities in modified gravity theory, so it motivates research in both directions.
The project I'm working on is part of the program of gauge gravity duality, and it's a realization of the holographic principle. In 1993, Professor Hooft proposed that our three-dimensional world with quantum gravity is equivalent to some two-dimensional worlds which does not know anything about gravity, which gave us some new insight in the nature of quantum gravity.
Distances. Type 1a supernovae are massive stellar explosions that can, for a few weeks, outshine the stars in their host galaxy. And they're interesting from a cosmological perspective because they're all the same brightness. And when you know the brightness of an object, and you can identify it by other means, you can work out how far away they are. Basically, that gives us a ruler to measure the universe. So you've got something to measure something, but why should one ruler be the same length as any other? Why should one be as bright as any other? And if they're not, what does that mean for what the universe contains? We don't know. That's why it's so exciting.
Today, Professor Hooft is going to explain to us about the Higgs particle and how particles get mass. So this is a very exciting period because the Higgs particle was just discovered at CERN in Geneva a couple of years ago, and this generated a lot of excitement in the field.
We knew that the Higgs particle would be quite heavy, about as heavy as the heaviest particles that had been already detected. But the Higgs particle itself turned out to be notoriously difficult to observe. So the precursor of the LHC machine was the so-called lab machine in the same tunnel where electrons and positrons were colliding. There they hoped that the electrons and positrons would also produce the Higgs particle. No such luck. Their energy was just not quite enough to produce the Higgs particle. But now they had the LHC machine, the most powerful machine in the world. It was decided that that machine should be powerful enough to detect the Higgs particle. What happens is that 1 in a trillion collisions would give a Higgs particle. When it's produced, the Higgs will decay. But it all depends on the mass of the Higgs, which we didn't know. So it was quite hard to do a measurement when you don't know the mass of the particle that you want to detect. So they scanned the whole spectrum, and eventually this was the kind of curve that was finally found 2 years ago. And when you look at the mass value of 126, then you find a tiny little hump in here. That's the Higgs. If there were no Higgs particles... With the discovery of the Higgs particle, we have now a standard picture of how all the particles inside an atom interact. However, we know that this standard picture, beautiful as it is and universal as it seems to be, is not complete. We do know things are missing, we do not know what exactly. But we do know that the theory we have today isn't airtight, it has open endings in it, there are mysteries, there are unanswered questions, and there are even some indications that more particles exist than the ones we know about.